Good morning or afternoon, ladies and gents. So, after our lovely stint with probability, we're going to officially move on to our next topic, vectors, or specifically, vectors in the plane. Now, I'm not going to lie to you, ladies and gents, the content we'll be doing will be a little bit more strenuous, not with respect to the maths, but more because there are quite a few different subtopics based within vectors. So like anything, we'll start with the basics and then we'll work our way from there. So for today's lesson, what we're going to try and do is effectively understand the concept of a vector and recognize how to apply the basic operations on vectors. Now, in year 7 onwards, and I know this because I taught this in year 7 forces or physics, a vector is a quantity which represents both magnitude and direction. Now, why I say year 7, you guys have to look at forces such as push-pull, and therefore you need to recognize force. And then obviously from your continuous junior years, the velocity and displacement. You're most likely going to see a lot of overlap between this and physics because obviously you see vectors within physics. So let's keep on going. One thing to note as well though, a non-vector is called a scalar. Now this is a key thing because we are going to be doing some things with scalar later on. And some of the key examples in this which we see across the board include speed, temperature, and distance. Obviously they are things that clearly change. Now you're going to see with one of the key representations, especially when you look at our textbook questions, how you represent a vector is usually by an arrow pointing in the direction of the action. So vector is the arrow there. So effectively, if you wanted to show a vector between point A and point B, you put the arrow through, and its simplified version is just AB. You're going to note that with most of my questions and examples, however, I don't usually use the arrow across. Instead, I'll do what some other textbooks do and put a curved underline underneath our letters. There's a few different ways of writing vectors themselves. You will actually see this in many different textbooks, including the ones I've put up there. But I digress, let's carry on. When you're sketching a vector, there's 3 different forms that they usually portray as. And this is something that's going to link into a lot of the questions, and a lot of the time people make the little mistakes because they don't read the question itself. First up, we have to recognize the bearings. Now you guys should know, especially from observing the year 12s doing it, vectors fit onto a Cartesian plane. Y, X. But there's 3 different versions of vectors. We can look at either compass bearings, north, south, east, west. And when we do this, we recognize that the angles don't begin at the bottom here, like they would with a mathematical one. If they are from the north and they're going northeast, they bear down towards the east, or respectively for northwest, down towards the west. Vice versa when you're going south. If you haven't done anything based with compasses, I promise you it's something that we touch on, but you'll see more mathematically later in. Next, true bearings. So for this one here, guys, it's very similar to what we've done previously, except instead of working all the way around, we're working more so in an in a clockwise motion. So we start at 0 or 360 here. We go across to 90, 180, 270, back to 360 or 0. So reading the question, if you had something that said a bearing of 170 degrees north, you would not go across to your second quadrant like you usually would looking at a Cartesian plane. You'd be beginning by going down and going into a 4th quadrant here. The final one, mathematical angle. Easiest one because everyone remembers it here, going in an anti-clockwise direction. Start at 0, across to 90, 180, 270, all the way up to 360. When reading questions or examples, please keep an eye on whether they state compass, true, or mathematical bearings. Because you will see in a couple of my examples, I'll show you the little mistake itself. If you pick the wrong one, then you've got to go back and do your work. So first up, let's look at our very first example here. All we want to do for our example one, sketch the following. So we want to sketch these different types of vectors across different fields. Oh, sorry for the rudeness there. Let's try that. So we've got a vector 3 kilometers at north 30 degrees east. So we draw up our Cartesian plane. Instead of putting y and x on it, you could put out north, south, east, west bearings. I haven't, but I think you can clearly pick it for yourselves. Begin at north, go across 30 degrees, place your vector, include your angle, 30 degrees, and your distance, 3 kilometers. For example, 1b, 2 meters per second at south 40 degrees west. So with this in mind, we begin south, we move up 40 degrees towards our west, and we show our distance, or in this case, 2 meters per second at 40 degrees. Next one along, 8 newtons at 100 degrees true. So remember with true, you start at our point here and work your way down clockwise. 100 degrees, put your vector, 8 newtons. It continues on. 25 centimeters at 330 degrees true, all the way around to 330, put in your centimeters. 98 newtons at 30 degrees. Because it's not stating anywhere that we're using true or compass, you must assume it's beginning at a mathematical angle. 30 degrees, 98 newtons. This last one's a little bit tricky, but you're going to see this is the one that kind of messes me up every now and again, and it may mess one or two of you guys up too. 18 meters at negative 100 degrees. Because we're looking on the Cartesian plane, if we did positive 100, assuming due to the lack of information that we are using a mathematical angle, positive 100 would go up across like this. Therefore, negative 100 begins and works our way down here, placing our arrow, our angle of 100 degrees, just facing the opposite way for the negative, and then putting in 18 meters. Now, with respect to the forms of the vectors, there's two different ways of displaying them, Cartesian and polar. We're going to get onto our polar forms in our next lesson. So let's start off with our Cartesian plane here. So, more often than not, if you're drawing it on the Cartesian plane, well, you guys should already know vertical would represent our y components, horizontal represents the x. So if you've got a vector, well, it's a bit tricky, but let's represent our vector as lowercase v with that little squiggle. To try and find its coordinates, we have to identify our x and go up by our y. So in this case, x is the x component, y is the y component, v underline is the vector, therefore v equals x, comma, y. Just like you would with plotting any point within the Cartesian plane. Later on when we get to our matrices, and if you've never seen this before, it's something you'll touch on later in your years. V for vector equals, and you just label them top to bottom. X for our x component, y for our y component. So for our next example, sketch the following vector v equals 3 and negative 2. 3 represents our x component, negative 2 represents our y component. So to show it here, there we go. We draw up our Cartesian plane. We go across 3 because it's our x component, and down 2 because it's our y component. Draw in our arrow, represent the V for vector. There is another way of writing it in Cartesian form, and this is something, again, you'll have clearly seen from our 12s literally across the room. I and J notation. It's the same principle. I, or AI, represents the X component. BJ represents the Y components. So with our third example, sketch the vector V equals negative I plus 2J. Just imagine that as if it's X equals negative 1, Y equals positive 2. So you draw it up, X equals negative 1, Y equals positive 2. Draw your vector, put in your V with a line underneath. That's all you need to do. For our final example in this lesson, I'll stop us just here. For the vector U, it is defined by the directed line segment from coordinates 2, 6. I know my handwriting's terrible, I'll just say it. 2, 6, 2, 3, 1. If the vector U, so U with a little underline, equals A, B, find A and B. So for this one, we know we're going to be using a matrix style Cartesian form vector. The reason states it here. We know that to actually represent our coordinates, it's going to have to be A1 plus A2. So A1, A2, plus B1, B2. B1, B2. Oh, my apologies, opposite way around, because we're beginning on one side and to the other. This then becomes 3 to negative 2, 1 to negative 6. And what we do is we just add these together to get our A and Y points, looking at it just here. So 3 plus negative 2 equals positive 1. 1 plus negative 6, equals negative 5. Because of how they are represented here, and because of what we've previously seen, especially in the matrix form, we can determine that A equals positive 1 and B equals negative 5. That's it for our first lesson, ladies and gents. Jump onto your questions and we'll get straight into polar form next lesson. Thank you very much.